Hello and welcome back. Today's topic is going to be on Schrodinger's idea of where electrons are. And if you think about them as being an address, it's going to help you out with this topic a little bit more. So think about what you know about an address and how that helps you get mail to where it needs to go, right? So Schrodinger and Bohr were kind of the same. They both talked about electrons having energy levels. And they both said in order to move up, you need more energy to go up to the next energy level, right? And so both Schrodinger and Bohr have the same basic concept of certain amounts or these quantized energies needing to put electrons in their place, for lack of a better term, right? And he called this quantum theory, where Bohr thought electrons orbit in these neat little orbits, right? That we're still drawing right to this day. But Schrodinger described them as more like probable locations. And the picture here is a very good indicator or a very good analogy as to what those probable locations are. So we have our windmill right there, right? And we can take a pretty educated guess that there's probably 3 fins on there, right? 3 propellers. And even though we know that, we cannot with this picture determine where they are. They're moving too fast, right? We can see them. They're making up this structure, this sphere that we see, but we do not know at any given time where they are exactly. And that's exactly what Schrodinger said that electrons are doing. They're too small, they're too fast, and so we really don't truly know exactly where they are, but we have these locations. We know they're housed in these certain energy levels, right? And so that's still kind of the same. And so that's what we're going to describe today, right? One of the main differences is that they're not always like these perfect little circles. Sometimes we get these pictures like this. And in this picture, what we're seeing right there are these certain energy levels, these certain areas where electrons are said to be. So instead of being like a big old sphere right here, these electrons just have a more defined area. Okay, and now I'm not gonna make you draw that this year. We just want to know kind of what those areas mean and really where like that shape would be on the periodic table, because the periodic table really gives us all this information. All right, so here's kind of a breakdown. Here's what I want you thinking as we break down all 4 of these, right? And if you think about these in this way, you're going to be good. So if we talk about trying to get a letter to Santa, right, or trying to mail a letter anywhere, we need 4 different things usually, right? First of all, we have this broad definition of where you are, and that is the state, right? So if you think about something you need in the address for a letter, state is something that we always put on there, like, all right, we always put MN for Minnesota, all right? Well, think about that as the energy level. Okay, and so these are kind of like Bohr's rings. This is the period number, right? In general, it's 1 through 7, right? As we build those out, we create greater and greater energy levels from level 1 to level 7 way on the outside, kind of like we've done up into this point, right? So if you have the state, if I say I'm from Minnesota, right, you have a better defined area where you can send me the letter, right? But that's a lot different than if I'm Rhode Island, or a lot different than if I'm California. Okay, so the size matters in that case, right? So then once we've defined what state we're in, then we can break it down to the city. So if I live in Minnesota, right, maybe I live in Duluth, maybe I live in Cotton, maybe I live down in Minneapolis, right? Those are all varying sizes of cities. And that's what we call our sublevels. So if we know what state we're in, then we can break it down into different cities with different sizes. S being like a really small city, like Cotton. F would be a huge city, like a metropolis, like the Twin Cities area. Okay, and then P and D would be somewhere in between. And again, if you go back to your periodic table maps, I had you draw those in there so you know the basic locations of where those are. So once we get our city and our state, that's great. We're having a better defined area. But if we only have a city, which is a more defined area. If I said I lived in Duluth, all right, you could send a letter to Duluth, Minnesota. You could also send it to Duluth, Georgia, right? And so we need both of those in order to really know where our letter is going to go. Once we know the city, then we can break it down even further and know the streets, right? And so that's what we call our orbitals. So our orbitals are the number of streets within that city, ranging from 1 to 7. right? And they're always odd numbers. So 1, 3, 5, 7 are the number of orbitals, right? And so small cities generally have less streets, like Cotton might have 1 street that goes through it, or in this case, Minneapolis might have 7 streets that go through it. Obviously, that's a little off, but that's the idea that we're taking a look at. So we have our state, we have our city, and then we have our street. And then to define that to the last extent is we also need our house number, right? So if I live in Minnesota, in Duluth, on Lindahl Road, you also need to know specifically where on that street I live. And in Schrodinger's case, for his quantum numbers, there's only 2 house numbers per street, right? And that's what he calls a spin. And his spin is either up or down, positive or negative, right? Those mean the exact same things. It just depends how we draw them, how we want to look at them. And so with these 4 numbers, right, that house that we're trying to get our letter to, there's only 1 spot for it to go. It can't get screwed up. And really what we're saying is that's what electrons do. Every electron for every atom has a different number, has 4 different numbers. And once we know those 4 different numbers, we could go we could put that electron exactly where we need to go. All right. And so that's the idea behind these 4. All right. So let's carry on. So here's kind of the whole thing in a nutshell. We have N's and L's and M's and S's. All right, we're going to take a look at all those. All those are just the same things we just talked about. And so this is kind of everything you would ever need to know. But there's no point in memorizing it because we're going to get this from our periodic table. Okay? And so the first number, his first number is the quantum, or his first quantum number is a principal quantum number, right? He gives that the symbol of an N, which is the main energy levels, which is our state, right? And so when we're talking about this, we're talking about the state. We're talking about the biggest, broadest definition of where electrons could go. And so to make that even easier, just think of it as the rings right now, the rings of Bohr's model, okay? And that'll make it easier. And they basically give it to you on the periodic table. And right, and these range from 1 to 7, with the bigger ones, the bigger number being like actually a bigger size, and those bigger sizes have more energy. They need more energy to keep those electrons in. All right, and so that's a principal quantum number. And in order to take a look at that, we're gonna go over some of these. We're gonna have 4 of these same slides. We're just gonna try to pick out what the principal quantum number is, or later on some of the different numbers for each of these same elements, right? So to do this, we're gonna look at where lithium is. So you need your periodic table here. Right, so lithium would be sitting right here, okay? Now, if I want the principal quantum number, all right, that's what this one's built up on. Basically, it's this number out in front. So the principal quantum number for lithium would be 2. All right, if I want to find oxygen, I just got to find where it is. Oxygen would be right here. So oxygen also have the principal quantum number 2. All right, if I want to do silicon, right, I just got to find where silicon is. And for silicon, I would drop down to right here, right? So silicon's quantum number would be, that's right, it would be 3. And potassium, if I found potassium, potassium's quantum number would be, if potassium was right here, it would be 4, right? And so it's not that bad. To find the principal quantum number, it's really just understanding what I'm asking you. To find that N, it's really just, in general, it's this period number out here. All right, so we'll come back to that. So if I said, hey, tell me an element that is principal quantum number 6, you would just go down here and you'd find anything that has a 6 in it. Now you can see there's some slight variations when we get in here. We'll talk about that later on. All right, so that's easy. The principal quantum number was the N, right? That was our state. Now we're getting into our city. So once we know what state we're in, right, then we can break it down even further. And so we kind of have this picture up here. So here's our state, here's our rings, but what we find out is in each of those rings are kind of broken down a little bit more, which is why we call it our sublevel, right? So each of those rings is broken down, and they're not always just rings, right? These rings actually have certain shapes, and that's what we're going to get here. So where our principal quantum number was N, the sublevel is indicated by an L. So we're going to have N and then an L. All right, so our city and then our state. And these shapes, we call them S, P, D, and F, right? And those S, P, Ds, and Fs are, again, they're found on your periodic table. Hopefully you have them highlighted. Now, in order to find those, right, once we know our n, right, once we know our principal quantum number, you just take that n and you subtract 1 from it, and then it's that number and anything lower. Okay, so if I had an n, if I had a principal quantum number of 3, I could have a 2, a 1, or a 0. Okay, that's what that would mean. So you can have this and any number lower is what we get out of this. And so when we go there, right, these all have certain number of shapes. So what I have, if I have an L equals 0, I know I'm a sphere, right? I'm an S, I'm a sphere. And so you know those are on your left side of your periodic table. If I find out I have a 1 included, I'm a P or a dumbbell shape, okay? If I have a 2, I am a D or a double dumbbell shape, okay? And then if I have a 3, get out of here, okay? I would have an F, come on. No, go back. Okay, I would have an F, or what I like to call a fancy. That's not really the real term, but we don't use them that much, and because it's an F, we'll just call it a fancy, and that'll be fine. Right, so basically, here are Schrodinger's numbers, right? 0, 1, 2, 3, and here are the shapes that we give them, S, P, D, and F, which we can find on the periodic table. So it's not really us memorizing these numbers. Really, we know where these are already, but Schrodinger liked to use numbers, which does make it a little bit easier in the long run. But we have sphere, dumbbell, double dumbbell. Those are the 3 that you have to know, and I'm going to show you those shapes in a second. So basically, if we end up with a 2 for my L, we also would have these shapes underneath it. So if we came up here, if this was my double dumbbell out here, I would also have a dumbbell and a sphere on the inside of me. That's kind of the way these build up. And you can kind of see that from this picture up there, even though they're not showing you those exact same shapes. Okay, so let's do that on this, and this is a perfect example of a periodic table. So if we already knew our principal quantum number, right, which for lithium was 2, then we want to find our sublevel. Well, that's why I had you outline it, because then you just know. So if lithium is right here, our sublevel is S, right? And S's are zeros. So we could say it's Schrodinger's number 0, which is indicated by an S. Okay? Oxygen. Again, principal quantum number 2, it's way over here. It would be a P, or the number 1. Okay? And we can see that if we reference back here, what I'm saying is I'm just giving you both of these, right? So S equals 0, P equals 1, D equals 2, F equals 3. If I go on to silicon, I know silicon's down here. So like oxygen, silicon would be a P. Okay, it would be a 3P, but it would be a P. And then potassium, down right here, that would be an S. So its outermost shape would be a sphere. Anything over here would be a sphere. Anything over here, its outermost shape would be that dumbbell, right? Anything right in this group, this would be a double dumbbell. Those excellent things. And then the fancy ones would be all the way down here. All right. So these are those shapes, right? And generally, you always have most of these, right? You're always going to have some sphere, but it might not be the one that's on the outside. Sometimes you have a sphere. Sometimes you have a dumbbell on the outside. Sometimes you have a double dumbbell. And then these are the ones we call fancy. And they have a bunch of different pictures. Those are the ones that, you know, if I gave you a picture, you would see one of these 3, just so you have an idea what it looks like. All right. So the third quantum number is called orbitals, right? So these are the streets. Now, out of all of them, these ones have the most involved with them, right? So we've gotten more and more involved up through the third number because they're more and more specific, and then our fourth number is actually a little bit easier. So in order to get the number of orbitals, right, we need to know what sublevel we're in. So if I know the sublevel, which is my L, I just take my, we should switch this, I should take my minus L and up to my plus L. And so that doesn't really make a lot of sense, but that's what my orientation is these are Schrodinger's numbers. This is how we come up with it. So if my quantum number was my second number was a 1, right? So my L was a 1, I'd have -1, 0, +1. If it was a 2, I'd have -2, -1, +1, or 0, +1, +2. And so we get that down here. So S's, they're spheres, right? There's only one shape that a sphere can take. So those are why those are always zeros, right? If my L's a 0, right, which is the sphere, then my M has got to be a 0 also. which means that I only have one shape. There's only one spot where those electrons can go, right? It's a one street city, okay, is what that means. My P's, these are a 3-street city, right? So there's 3 streets in my city, and so in order to name those streets, I have a -1 street, I have a 0 street, and I have a +1 street. That's what that is. These are just the names of our streets, right? If I live in a bigger city, if I have 5 streets, if I'm a D and I have 5 streets, right, that means my L equals 2. And so to go from -L to +L, I'd have -2 street, -1 street, 0 street, +1 street, +2 street. And just like you said, or just like hopefully you're thinking, is if I go all the way down to my F, right, I have 7 different streets. So these would be our biggest cities. All right, and since L equals a 3, I'd have -3, -2, -1, 0, +1, +2, +3. And next week, we're gonna use these numbers again, and they'll kind of make a little bit more sense when we put it all together. But that's what those numbers are. That's what they mean, and that's where they come from. All right, so we'll do that, and we can see that I have a little bit more detailed map of the periodic table right now. To help you out. And the only way I'd ever ask you these questions, I'm not going to this year, is by giving you this one. You don't need to write all this on your periodic table. So what would the orbital, right, what would the M for these elements be? So if I'm lithium, and I know lithium's right here, right, my principal quantum number is 2, my sublevel is S, and then so my orbital is that number L, or that number M, sorry. And so that is always a 0 because I only have 1 street. So over here I have 1 street. I can have 2 houses on that 1 street. We're going to talk about that next, but I am the 0, right? If I'm an oxygen, I'm over here, right? So my oxygen would have the number, and this is why we need this one, it would have the number a -1, right? So right here you would have the number -1. So I live on -1 street. Okay, what does that mean? Doesn't matter right now. As long as you can look at this and use it as a puzzle map, you're good to go, right? And so I live on -1 street, okay? And then I have my silicon. Again, silicon is right here. And so silicon would be principal quantum number 3. It would be a P, right? And then it would live on 0 street, okay? That's all that means. And then potassium, last one over here. And that would be, again, principal quantum number 4. It would be shape S or sublevel S, and then it would also live on 0 street. Okay, and so you can see there's lots of zeros, lots of -1s, and not as many of the 2s and 3s because we only get to 3s when we get down here. All right, so that's how you look for them, and these are what the shapes look like. So spheres, there's only one way in 3 dimensions to look at a sphere. That's why there's only 1 street, right? There's 2 electrons that can be in that shape, right? For the dumbbells, right, for the P's, we can look at it in the X, we can look at it in the Y, and we can look at it in the Z. Now you don't need to know that. This is just where we give our -1, our 0, and our +1, right? We just give it street names is all we're doing. And so I can have 2 electrons there, 2 electrons there, and 2 electrons there. All right, those are my 3 streets. And you can see the same thing with D. So we have 5 streets for D. We have 5 different shapes orientated in different directions, right? And again, in all of these, there can only be 2 electrons in all of these, is what we're getting to. All right, last and easiest, right? The fourth is called the spin. This is how many houses we can have per street. And the answer is 2, right? You can have only 2 electrons on each street, okay? You can only have 2 houses on each street. You can only have 2 electrons in each orbital, right? And so this is your fire number, right? The numbers for your house. So once we have our state, our city, and our street, you can either be a +1/2 or a -1/2, right? And all that is the spin. This is the last quantum number. You're either a plus or you're a -1/2 for your spin. And so if we did that, again, I wouldn't ask you to do this, but if we did it really quick, lithium, again, we go to lithium and we look at this one. Oh, everything on the left is a +1/2 first, right? So we'd have a +1/2 spin. We'll draw that out later. Oxygen, if we go right here, it'd be a -1/2 spin because this group right here would be -1/2 spins, right? If we go to silicon, that's right here. It would be a +1/2 spin. And if we go to potassium right here, that would be a +1/2 spin. And so you can see based on these numbers right here, here's our spins. You could see positive, negative, positive, negative, positive, negative, and positive, negative. All right, and that's a breakdown. We can see that as we get bigger, right, we get those shapes, and we can go from there.